Sun's stronger waves are away. But perhaps you will ask, if no one has ever seen these waves, nor the ether in which they are made, what right have we to say they are there? Strange as it may seem, though we cannot see them, we have measured them, and know how large they are, and how many can go into an inch of space. For as these tiny waves are running on straight forward through the room, if we put something in their way, they will have to run around it, and if you let in a very narrow ray of light through a shutter and put an upright wire in the sunbeam, you actually make the waves run round the wire, just as water runs round a post in a river, and they meet behind the wire just as the water meets in a V shape behind the post. Now, when they meet, they run up against each other, and here it is we can catch them. For if they meet comfortably, both rising up in a good wave, they run on together and make a bright line of light. But if they meet higgledy-piggledy, one up and the other down, all in confusion, they stop each other, and then there is no light, but a line of darkness. And so behind your piece of wire you can catch the waves on a piece of paper, and you will find that they make dark and light lines, one side by side with the other, and by means of these bands it is possible to find out how large the waves must be. This question is too difficult for us to work it out here, but you can see that large waves will make broader light and dark bands than small ones will, and that in this way the size of the waves may be measured. And now, how large do you think they turn out to be? So very, very tiny that about 50,000 waves are contained in a single inch of space. I have drawn on the board the length of an inch. Now I will measure the same space in the air between my finger and my thumb. Within this space, at this moment, there are 50,000 tiny waves moving up and down. I promised you we will find in science things as wonderful as in fairy tales. Are not these tiny invisible messengers coming incessantly from the sun as wonderful as any fairies? And still more so when, as we shall see presently, they are doing nearly all the work of our world. You must next try to realize how fast these waves travel. You will remember that an express train will take 171 years to reach us from the sun, and even a cannonball would take from 10 to 13 years to come that distance. Well, these tiny waves take only 7 minutes and a half to come the whole 91 millions of miles. The waves which are hitting your eye at this moment are caused by a movement which began at the sun only 7.5 minutes ago. And remember, this movement is going on incessantly, and these waves are always following one after the other so rapidly that they keep up a perpetual cannonade upon the pupil of your eye. So fast do they come that about 608 billion waves enter your eye in one single second. I do not ask you to remember these figures. I only ask you to try and picture to yourselves these infinitely tiny and active invisible messengers from the sun, and to acknowledge that light is a fairy thing. But we do not yet know all about our sunbeams. See, I have here a piece of glass with 3 sides, called a prism. If I put it in the sunlight which is streaming through the window, what happens? Look, on the table there is a line of beautiful colors. I can make it long or short as I turn the prism, but the colors always remain arranged in the same way. Here at my left hand is red, beyond it orange, then yellow, green, blue, indigo or deep blue, and violet, shading one into the other all along the line. We have all seen these colors dancing on the wall when the sun has been shining brightly on the cut glass pendants of the chandelier, and you may see them still more distinctly if you let a ray of light into a darkened room and pass it through the prism. What are these colors? Do they come from the glass? No, for you will remember to have seen them in the rainbow, and in the soap bubble, and even in a drop of dew on the scum on the top of a pond. This beautiful colored line is only our sunbeam again, which has been split up into many colors by passing through the glass, as it is in the raindrops of the rainbow and the bubbles of the scum of the pond. Till now we have talked of the sunbeam as if it were made of only one set of waves, but in truth it is made of many sets of waves of different sizes, all traveling along together from the sun. These various waves have been measured, and we know that the waves which make up the red light are larger and more lazy than those which make violet light, and that there are only 39,000 red waves in an inch, while there are 57,000 violet waves in the same space. How is it, then, that if all these different waves making different colors hit on our eye, they do not always make us see colored light? Because, unless they are interfered with, they all travel along together, and you know that all colors mixed together in proper proportions makes white. I have here a round piece of cardboard, painted with the 7 colors in succession several times over. When it is still, you can distinguish them all apart, but when I whirl it quickly around, see, the cardboard looks quite white, because we see them all so instantaneously that they are mingled together. In the same way, light looks white to you because all the different colored waves strike on your eye at once. You can easily make one of these cards for yourselves, only the white will look dirty because you cannot get the colors pure. Now, when the light passes through the 3-sided glass or prism, the waves are spread out, and the slow, heavy red waves lag behind and remain at the lower end of the colored line on the wall, while the rapid little violet waves are bent more out of their road and run to the farther end of the line, and the orange, yellow, green, blue, and indigo arrange themselves between according to the size of their waves. And now you are very likely eager to ask why the quick waves should make us see one color and the slow waves another. This is a very difficult question, for we have a great deal still to learn about the effect of light on the eye. But you can easily imagine that color is to our eye much the same as music is to our ear. You know we can distinguish different notes when the air waves play slowly or quickly upon the drum of the ear, as we shall see in Lecture 6. And somewhat in the same way, the tiny waves of the ether play on the retina or curtain at the back of our eye, and make the nerves carry different messages to the brain, and the color we see depends upon the number of waves which play upon the retina in a second. Do you think we have now rightly answered the question, what is a sunbeam? We have seen that it is really a succession of tiny rapid waves, traveling from the sun to us across the invisible substance we call ether, and keeping up a constant cannonade upon everything which comes in their way. We have also seen that, tiny as these waves are, they can still vary in size, so that one single sunbeam is made up of myriads of different sized waves, which travel all together and make us see white light, unless for some reason they are scattered apart so that we see them separately as red, green, blue, or yellow. How they are scattered, and many other secrets of the sun waves, we cannot stop to consider now, but we must pass on to ask, what work do the sunbeams do for us? They do two things. They give us light and